Hello everyone, my name is Juan Merlos. I'm a PhD student at Florida Atlantic University, and today I will be presenting my research work this summer at the SPARK internship. This work revolves around using cameras for AI systems and how to make these cameras more robust in situations of varying luminances. So lighting is not something we usually think about that can affect an AI system, but it can. An example of this would be if you are inside of a dark room and you walk outside, usually your eyes will have trouble adjusting. Cameras, kind of the same thing happens with cameras. If you have a camera focused into a dark room and there's a very bright outside area, a traditional camera can really only focus on the dark area or the bright area. If you try to see what's in the dark area, the bright area will appear as like a bright blob. And if you try to focus on the outside, the dark area will be way too dark. You won't be able to see anything. So there's these kinds of cameras called HDR cameras, high dynamic range cameras, that capture detail in both very bright and very low light environments simultaneously using 32-bit capture many of the times. This is different from low dynamic range cameras, which capture at an 8-bit pixel precision. The issue is we want to use these cameras in robust lighting scenarios with AI systems. One of the issues that arises is that traditional AI systems are trained on lots of 8-bit imagery, generally because this imagery is what's widely available. Most consumer cameras are 8-bit, and therefore most machine learning models, computer vision models are trained on 8-bit images. In order to further the Army's goals of developing robust and efficient AI systems that can detect objects and detect semantic information in varying lighting environments, we would like to use HDR cameras and HDR imagery together with computer vision models in order to kind of make detections and kind of extract information in any kind of lighting environment. This leads us to tone mapping. Tone mapping is the process of converting an HDR image into an 8-bit or a lower dimensional image. This has generally been around for a very long time. HDR imagery can be converted into 8-bit for example, display on a monitor that's 8-bit. This has generally been done for a human consumer, so HDR imagery is tone mapped down into 8-bit for a human to view. So tone mapping algorithms have generally been put together in such a way that it makes a smooth image for a human viewer. But now what we're seeing is that we really want to use HDR imagery for a machine viewer, not a human viewer. We would like to feed it into a computer vision model. The issue arises is if we feed a traditionally tone-mapped image into a computer vision model, a lot of the information gets distorted, and the computer vision model can't make accurate detections. It can generally make more detections than if you would feed a low dynamic range image, but especially in complex lighting environments, but you still lose a ton of information just from the compression of the 32-bit HDR image into the 8-bit low dynamic range image. So this project is mainly focused on creating a tone mapping algorithm or ways to take the 32-bit HDR image and feed it into a computer vision model that's meant for 8-bit information in a way that we can extract all the objects and all the semantic content from the 32-bit HDR image. One of the ways we did this is by something we call the multiple exposure proxy. So we take an HDR image, 32 bits, and we segment it into different luminance bands using logarithmic tone mapping. So these bands are basically just 8-bit chunks of different exposures. Some of the exposures are for the very bright areas of the image. Another one is for the very dark area of the image. And we have multiple of these. So we basically take the 32-bit input and segment it into different 8-bit images that captures detail at different points of lighting within the image. We then pass each of these different points through a machine learning model, a computer vision object detection model in this case, and we get detections from each of the exposures. One of them will be detecting things from the very bright areas, one of them from kind of the middle ground, and then another one from the very darker areas of the image. And then all of this gets put together using non-maximum suppression, which will combine all the bounding boxes into one coherent image. This basically allows us to combine object detections from multiple exposure bands into one. There's been some previous work on this area, and we've kind of expanded this into object segmentation, object tracking, as well as other tasks using kind of this approach. as well as streamlining other methods that enable this to work at a lower complexity. So kind of putting all this together, If you use the multiple exposure proxy method, so combining all of the luminance bands and the detections from each of those luminances, and you compare it to a traditional tone mapping operator, like Reinhardt, for example, in instances where the images are very flat, there's not that much lighting change, results are kind of similar for both. They both achieve similar object detection performance. However, as lighting conditions get more complicated, you can think of like a forest, and there's very bright lights shining through the trees, but there's still very dark, shadowy areas. Situations like that, when we process all of these images and we get object detection results, for images where, once again, it's like a very flat environment with not that much lighting change, results are pretty similar. But as soon as the lighting scenarios get more complicated, traditional tone mapping operators like Reinhardt see about a 20% reduction in MAP performance. However, by using multiple exposures and attaining object detection results from different exposures, we see that it remains relatively stable. And actually, by using the multiple exposures in complex lighting scenarios, we get about a 20% boost to MAP, model object detection performance, as opposed to using a traditional tone mapping operator. Utilizing methods that take 32-bit imagery and make it able to be fed into traditional computer vision models enables Army goals of robust and efficient AI systems that can perform in any type of lighting environment. This allows us to detect objects, track objects, segment objects in a wide variety of lighting conditions. And by making machine-focused tone mapping algorithms, it allows the computer vision model to see in any of the very bright or very dark areas near losslessly, as compared to human tone mapping, which will distort a lot of that information. Thank you.